And it's time. I think we can start. So if you're ready. So thank you very much everyone for participation. So we are today is a, let's say, hot or up to date the topic from high performance computing to quantum computing from Ilias Savvas. I really hope that I pronounce it correctly.
Yeah,
Forgive.
correct.
So,
Correct.
floor is yours. So
Okay,
thank you.
thank you. Thank you. First of all, hello everybody. Hello everybody from Larissa, from Greece, which is rainy today. And actually, I'm very happy to be here with you, even if it is like that, and not face to face. It's good for the economy of time you mentioned, but on the other hand, it's not so good for socializing. Anyway, this seminar, I think it's because it's according to a memorandum of understanding we signed, both sides, both universities signed 1 month ago, if I remember correctly. And the title of this seminar is From High Performance Computing to Quantum Computing. It actually is not a statement, it's a question. Few words about me. This is the agenda of this small talk. A little bit about some information about our university and our department, our main research interests, and how, if we are going to move from HPC to quantum. A few words about one scientific student group we have got in our department and an upcoming event that we are going to organize. And after that, I think that we will have a free discussion. Now, a few words about me. I'm a professor. I'm a dean of the School of Technology. The courses I teach are programming, data structures, algorithms, parallel programming, and from the next year we are going to introduce a new course which will be quantum programming. Our main research interests are HPC, high performance computing, with many topics like clustering techniques or point anomaly detections and regression classification. And the platforms we used up to now were distributed computing, cloud, cluster, multi-core computing. And currently, with a question mark, as I told you at the beginning, as I mentioned at the beginning, quantum computing. Our university, a few words about that, is now the third largest in Greece. It expands in 5 cities. Larissa is one of them, and we are in Larissa. There are 8 schools and 35 departments. We offer 72 MSc courses. And our school, the School of Technology, consists of 4 departments. You can see our logo in the right side of the slide. And one of them is the Department of Digital Systems, where we belong. Our department. Our department, we have up to now 15 number, the number of staff is 15. We have more or less 600 undergraduate students. We offer 2 MSc courses, one on software engineering for mobile and internet applications, and another one on modern telecommunication systems and the Internet of Things. We offer PhD in different topics, in many different topics, like software engineering or databases or HPC or radio propagation channels for millimeters and terahertz communications. And currently, we have our first PhD student in quantum computing, and the title of his thesis will be machine learning using complex quantum computing systems. And there is another one candidate. We didn't finalize the title of his PhD thesis. We're still working on the proposal, and we're probably open to discuss it with you at the end of this presentation. We've got in our department, we've got one computational cluster with 20 Linux machines, and we can easily expand it to 120. We use message passing interface, the MPI, for that. And we've got a private cloud based on Hadoop with 20 nodes and a lot of platforms already installed on it, like HBase or Hive. And of course, we have 2 labs for networks and telecommunications. I don't know exactly what they are doing there, but I know that these labs exist. Now, our question here is from HPC to quantum computing. Why to do that? Have in mind that our main research interest was on high performance computing, and quantum computing was something new for us. Newer. We didn't know if it is theoretical without practice in real world applications, or if we apply cloud computing, quantum computing techniques in real cases. I remember that 4 or 5 months ago, we've got this conversation with Andrei, and suddenly, and this was a big surprise for me, 10 months ago, an undergraduate student of mine asked me to be his supervisor for his last year dissertation on quantum programming. It was a big surprise for me. And then actually, yes, then the journey begins. A lot of time, we spend a lot of time to write quantum programs at the beginning in simulation environments, and then we moved to real machines, and actually we used the IBM quantum devices. And then suddenly, when we tried the same programs, we used them in simulation on a real machine, instead of solid results, we obtained results with probabilities. That was our first surprise. It's not a surprise anymore, but for the beginner it was a big surprise. Why we don't have an answer that I have something like yes and no? And why to change? For example, there are already there are a lot of high performance computing platforms like cloud, like distributed, like clusters, like GPU computing nowadays. Why computing? Yes, there are many promises. Many promises. They say that quantum computing devices will save our world when they work, I suppose. But on the other hand, we have a large amount of investments, amount of investments of companies like IBM, Google, Intel, Microsoft, and so on. And we recently see collaborations of universities. Today morning, I realized that Edinburgh University, Glasgow University, and Strathclyde University from Scotland, they are going to spend around about $65 billion up to 2030 in order to do some research and for infrastructures on quantum machines. And of course, now we have a lot of tools, a lot of platforms and libraries which are already working, like Qiskit or Pickwheel, and they say that the time complexity of HPC from hours or even century, they will go down to seconds, if we believe them. But on the other hand, again, last October, Google announced that a quantum computing device solved the problem in 2 minutes and 20 seconds, when the same exactly problem supercomputer needs around 10,000 years. I don't really know what is the problem, but this is the Google's announcement. I don't know the algorithm, what they've done, but we just have the results. And I suppose that we believe Google. Now, for quantum computing, what do we need? It's not that difficult. The only thing we need is Python and Jupyter Notebook, of course. On the other hand, if we want to use the IBM machines, we need the Qiskit package, which is supported by IBM. We've done a lot of experiments on both simulation and real devices, and when we say real devices, once again, I mean the IBM quantum computing devices, of course remotely. And again, Qiskit is a very powerful package because Qiskit supports a lot of applications like machine learning or cryptography and so on. And for us as beginners, the problem was the reliability of these machines, of these real quantum computing devices. And okay, we're talking all the time about quantum computing, but what's different here? What's interesting here? Actually, there are a lot of things. First of all, we don't use bits, we use qubits. And qubit is a vector, a two-dimensional vector. And combining qubits, another interesting thing, is that they provide us high-dimensional spaces, because they use this Kronecker product in order to combine qubits. And there are two attributes that was very exciting, at least: the superposition and the entanglement. First of all, the superposition. The superposition is when a qubit is both 0 and 1. at the same time. So that means that we have to play with probabilities. On the other hand, entanglement is when a quantum state in which two particles or groups of particles interact instantaneously. And that was very curious. We were very curious about that. And we wanted to test that. And we tested it, you will see. Of course, what we are unhappy is that we have to program on low level. We have to do with gates and circuits. We have to remember our student years when we were learning assembly or something like that. But if it works, again, they say that nothing is going to be the same in our world again. And the reliability, once again, is that what we have to test before we move from our our experience up to now to HPC to quantum machines. Now, in order to to investigate the reliability, we used a very famous algorithm for string matching, the Bernstein-Vasarany algorithm, and we tried a phrase, this WhatsApp doc, in order to see if a real machine will guess it correctly. We turned it to bits. That means that we have a sequence of 112 bits. That means, again, for one classical computer, we need 112 searches in order to find it out. But on the other hand, if our quantum computing device work well, one search is enough. Of course, if we have more than 112 qubits. So we tried it. We tried it on a real device with 5 qubits. It needed 28 searches, and the reliability is what we see here, 48% without calibration and 51% after calibration of the machine. If you think that this is not a good probability, actually it is a good probability and a very promising one. Just to be a little bit more specific, we will do the same with a smaller bit sequence of 3 bits. Suppose that we have a secret bit sequence, which will be this 101. We tried it on the left hand. You can see the code we needed to write in order to find it out. And of course, with just one shot, the probability of guessing the right bit sequence was 100%. But again, that was simulation. We turned it into a real machine. But before we done that, we need, first of all, of course, to have Python, to have Anaconda and the Jupyter Notebook, to have Qiskit, and to create an account to IBM Q Experience. This is very easy to be done. It is free. And then IBM provides us with a token. We have to copy this token to our program to run some commands in the Jupyter Notebook, like from Qiskit import IBM Q and so on, and to put this token over there in order to be recognized by IBM. And that is the result we obtained. Few more lines of code, like IBM load account, and which machine are we going to use? IBM, for that case, IBM 16 Melbourne. There are a lot of machines that are available from IBM. One problem is that we've got this answer not immediately, but we have to wait because they go to a queue. And that was the result we obtained. Okay, the guess was right. The bit sequence 101 had the bigger probability, which is actually around 64%. This is the real results obtained by this IBM machine. But the promising one is that the second largest probability is around 14%, and the third around 12%. And this is very convenient to be sure that the first one, this 63% or 64%, around 64%, is the correct one. So even if we don't get solid results, but just probabilities, after all these experiments we have done, we strongly believe that the results are correct. The only thing is that the only problem is that we have to turn it out to a more a more readable result, just to see probabilities. So that's a few words about quantum computing and if they are reliable. Now, 5 or 6 months ago, if I would have to answer the same question, I would say that, okay, those machines are not reliable. But now I think that, yes, they are reliable. The possibility, the probability of the right answer is very high. And the most important is that the second largest probability is very low. So that's it's very convenient to get the right output. Now, what else would like to tell you was that in our department we've got a student scientific group named Quantum Programming Group. There are a lot of students of our department, very enthusiastic. Yes, they're really very enthusiastic about this quantum programming. Up to now, the only thing they are doing is to explore well-known algorithms, and they try to develop some quantum games. And on the other hand, we try to be part of an ecosystem named Q, from Q World, and we will be a Q Greece, of course, but we are still under evaluation, and I think that by the end of February we will be part of this ecosystem, this Q World. As far as I know, I think that Q Russia is already part of this ecosystem. And finally, we've got an upcoming event we are going to organize. We are organizing it already, which will be an introduction to quantum programming. We call it workshop instead of workshop. And this is going to be a hands-on quantum programming, a practical introduction to quantum programming with qubits, quantum gates, construction and execution of quantum circuits, implementation of basic quantum algorithms, and so on. So if there are any one of you that wants to participate or to attend this event, you are very, very, very welcome. That's it from my side. I really want to thank Maria Budakova and Andrei Chernin for this collaboration. And maybe now we can proceed with discussion. I think that it's going to be a free discussion. For example, I have to maybe we have to extend our collaboration for example, co-supervision of PhD students. And of course, if we're going to do something like that, another memorandum of understanding is needed. Or maybe we can have common MSc programs, I don't know. So I believe that that's why we're here, because just to continue this collaboration. So that's for me. Thank you very much.
Okay, thank you. Dear colleagues, any questions? I would like to say that because we are very close to the real European Christmas, maybe we could have another seminar just early next year, but then we could do in vice versa mode. We could explain what we are doing.
Yes.
And our institution is just multidisciplinary. We have chemical synthesis. We have clearly very significant experience in nanocharacterization using synchrotron radiation facilities, free electron lasers, etc., etc. And we have working agreement with the main European, but now they are really the most important in the world. It is free electron laser in Hamburg, and DESI synchrotron in Hamburg. It is the largest synchrotron circle in the world, and also ESRF, European synchrotron in Grenoble. But also we just have a long-standing tradition of do supercomputer simulation of local atomic and electronic structure. and we use mostly density functional based theoretical approaches for understanding the local atomic and electronic structure of the nanomaterials. But we also use molecular dynamics and some other type of approximation. And just for 2 years, 2 years and a half, we are using machine learning for the analysis of the data. We are having mostly at synchrotron radiation, because now this large-scale facility produce big data. And clearly now it is not possible to use only PhD students to analyze them, because or we have to wait 10,000 of years, like you
Yes.
said about one of the tasks. Yes, and we are one of the first, maybe the second group, who start applying machine learning for X-ray absorption spectroscopy. It is a type of spectroscopy using at synchrotron radiation, and we also and this program for analysis data, it is now written with Python, and also use these notebooks you mentioned, you put etc. And clearly for us is very interesting, not at least from my point of view, but I do believe that our younger generation, they must be even more curious to apply something new, like quantum computing, quantum programming, and clearly it will be interesting for us. And to finalizing just general formal things, we just have signed agreement between our university by our rectors. But for example, later, if we found real something mutually interesting topics, because our experience could be really just very mutually interesting, because we are from different fields but looking at the same world, and we mostly, even in the title of our institute, it is Smart Materials. We are looking for any materials for different applications, starting from catalysis up to oncology application, like theranostics materials for oncology, etc., etc. And for example, we have good experience in combining joint PhD program. We have, no, it is in Latin cotutela diploma, means there are two co-supervisors for the same PhD, and PhD rotates approximately half year there, half year here. We have such a long-standing tradition with Turin University in Italy, and we just have 3 Russian guys who got PhD there, and we have 2 Italian who got PhD according to this joint project. And also from time to time there are some competitions for joint grant international, and we also could do something together. But clearly the first thing is to find the same topic that mutually interesting from both sides and start to do there. And what is really, I'm really interested in your presentation, that you show that in spite the probability is not 100%, but one could easily understand that this is the right answer. I do believe, I really say that I am like a person. I also do the same, because I really don't know the whole existing information. We try to make decision in the limited information we have. and we try to obtain the best. Thus mean human being also, we never feel that we know that our decision is 100% right. But we know that according to the information we have now, it is the best solution. And we live our life, and it is not tragedy for us that probability is not 100%. Okay, and this is for me is very. I'm happy about this thing. Okay, dear colleagues, who would like to ask questions or or to say something at least, please?
I can add a little bit concerning the search of some mutual topic. Thank you, first of all, for the very nice presentation, and for many of us it was like introduction to this field. Can you please specify what are the so what kind of task should it be that can be efficiently solved with these methods given the current limitations? So, for example, if we think about the task for machine learning, then we try to find something which has big data sets and some, I don't know, some hidden dependencies and so on. So what kind of task should we think of which will be ideal to try to solve together?
Okay, I believe that in this moment it isn't real. It is not realistic. Actually, there are some quantum machines with not so many qubits. This is the main point. This is the main problem, to have a lot of qubits and reliable qubits. And my personal opinion is that for the moment it's just research. We don't have these machines. And that's why all this large amount of money are invested now by these companies to build that kind of machines. On the other hand, applications, first of all, we have to be sure that the quantum machines will work together with the classical machines, with the classical computers. We cannot live without the classical computer. For the moment, talking about machine learning, mainly matching algorithms are these that are the most, for my opinion, the most well-known and tested. There is a lot of research there, a lot of research. I cannot answer that exactly. But on the other hand, what I noticed in your university, and talking about this PhD cooperation, co-supervision, is that there are a lot of things that we don't know about what you are doing. And we could combine easily applications of quantum machines on what you are doing, instead of searching on, okay, what application I will do, what is the real world. You are the real world, so you can drive us to, you can lead us to a real application. And that's what, after all, we wanted. No, we wanted to collaborate with you, because we don't have, our knowledge on what we are doing is zero.
Clear, thank you.
Or below zero.
And one more question. So you need to, from programming point of view, you need to write. So it's another logic, right, of
Yes.
an algorithm.
Yes, actually, it's more or less, as I mentioned before, you play with gates and circuits.
Okay, and is there a possibility to have kind of a simulator of quantum computer using normal HPC? So where you can, when you can try your algorithm and you say that, look, this task will be solved with my algorithm and this not, or this is better. So is it possible to make a simulator of quantum computer with normal computer?
Actually, there are simulators up to now, but we use the same language again, circuits and gates. If you want to go to a language like Python or C++, I don't know what you mean, the answer is no, there is not, that does not exist something like that for the moment. And then just think about that 60 years ago, we thought that the only language is assembly, right? And the things run, things change very fast now. I don't know if we had the same conversation next year, what we could say.
So I remember that if we use maybe not IBM supercomputer, but some of Microsoft, so you if you have account, you will have limitations of real use of quantum computers. But also I remember something like they just save some results of operator application on your qubit. So, okay, from physical point of view, I know that gates and gates are represented as operator that is applied to the quantum system.
Yeah.
So, and they may save them. So I remember that it's something in Microsoft. You may apply a real quantum computing algorithm to apply a new result, real new result, or just download result from previous run of one of the users.
No.
So, is it for IBM the same procedure, or you may just use this quantum computer without some limitations?
Actually, up to now, I didn't have any limitations. When we apply for a program, then we've been in a queue, and when our turn will come up, then we'll have the results. By what else we tried up to now is to get access from Rigetti, but we applied and we wait for their response for another company just because we want to compare things, not from Microsoft.
Okay.
Not from Microsoft. Yeah.
Okay. So, and also, if I could, one question about the probability of the result. So to be clear, for this picture on this slide, so you ran quantum computer several times to obtain the same result and collected probability. So that means that for this histogram, you calculate the same procedure more than 8 times. So, and
it's about 1,000 times.
Okay, it's a lot. So, and the probability of right answer more than half. The question is, if we are running a quantum computer, so probably in real life we don't want to run 100 times to calculate the probability or normalize the probability to check is it correct or not. So that means that from your introduction, the surprising of probabilities of answer means that if we do only one calculation, that we are not 100% sure that it's correct one.
Yeah, and actually, if you want, I can show you the results, the exact results about this WhatsApp phrase we were trying to.
Yes, for me it's not clear for which tasks we may apply the probability of our right answer. So maybe the prediction of electronic density seems to be something similar for that, but I just cannot imagine the example for real application of probable answer. So here is the quantum computing is applied for answer that have certain answer, like direct answer. But could you suggest or imagine the task where the answer might be obtained with the probability? I mean, more efficient obtained from the probability point of view than from real computer calculation, not quantum computer.
If you want to know if you will get a postdoc position after you finish a PhD, Oleg, or not, if you will have the answer 64%, then you are happy.
Okay. Okay, thank you.
All right. And,
Okay. Any other questions?
What else I wanted to say is that actually, with just one one search, the results are extremely promising. We didn't. There is no need to run it 1,000 times. Even with one shot, we got the right answer.
No, maybe if I understand it correctly, for example, for some tests, you have the probability, let's say 50%. But what is the probability if I, for example, run this task twice and I got the same result? What is the probability that this result is wrong? So can you say that, if I understand correctly, how we can interpret these probabilities?
What we noticed is that the second largest probability was very low. And that gave us the convenience that we've got the right answer. Because there is a big gap between the first and the second probability.
So there are many possible answers.
Yeah, as you can see here, there are all the possible answers.
Yeah, so Oleg, maybe this is the explanation. You can, for example, run twice your algorithm, and if you get twice the same result,
not
then,
exactly the same, more or less the same.
Yes. Then it's much more than 64% that this result is correct.
Yeah. I see. It's okay. It will works better than usual computing due to less time, so less amount of runs that you will apply. So for 8 possible answers, if you run it twice, you will obtain the good results and good probability. So my question was, could we interpret, let's suggest the task where we're interested in probability even? We don't want to know the real answer, but maybe probability of this answer. I mean, it's something similar to electronic density in atomic systems. Could we somehow predict, let's say, atomic electronic density? So, and work with probability directly?
I'm afraid I can't answer that. I don't know to answer that.
Okay.
I could suggest one task, for example. We discussed it just a day ago. We try to estimate oxidation state of europium in our nanocomposites for X-ray photodynamic therapy. And this could be 3 or 2. And if we would like to estimate this, we know the answer could be 2 or 3. And if we would like to estimate it from first principle simulation, it will be long enough, because these rare earth elements have a lot of multiplets, a lot of electrons, they are all correlated. It takes hours to reply. But if we need the reply 2 or 3, we could apply this quantum and we obtain the 3 is just 5 times more probability than 3 and 2. Okay, this will be, the problem will be solved. This is why I think that really in our research there are problems that have not only specific possible answers. Another task, for example, we apply in machine learning for analysis of histology in tumor. And we know there are possibility or one that is healthy, or for example, 7 other types of cancer. But they are numerated. For example, 7 possible answers. And this, if we apply to this problem, then we could obtain, okay, the most probable is this one. Because we know that the type of cancer could be A, B, C, D, F, and basta, and no at all. Thus, I do believe that there are one could find tasks where solution, if you said that this is the most probable and it is 5 times more probable than another solutions, this physical or chemical task just exists.
So, if I understand correctly, you mean that you applied techniques like classification or something like that in machine learning?
Yes, classification, yes.
Yes, so this is a good problem to be solved then, using that kind of technology. We didn't try that, but it's, yes, you have 5 or 6 or 10 different attributes, and you want to see which is the most important.
Yes, and we know that number of possible solutions are 1, 2, 3, 5, but not infinite. And we need to select the most probable. And we know that solution could be only this, or this. Okay. And for this information, the solution like this is the most probable and probability is 2, 3 times higher than for other is enough. For example, for medicine, it is okay. It works because we see this could be this disease, this could be COVID, this could be simple pneumonia, or this could be simple Koch. Okay, 3 possible solutions, and if we could estimate it right from theoretical analysis of data, it could be good enough.
Actually, from our point of view, from computer science, the first step is to understand exactly the problem. And the problem is, for example, what you were describing up to now. So that's why, at my final slide, I mentioned about common PhDs or co-supervision of PhDs, because we have to know the problem. We have a large data set, and this data set is this or that, or with these kind of attributes, and you want to extract that kind of information. So there's a lot of conversation about it. It's not that simple. We need to, we need to collaborate for that. I can't hear you.
So, and also a question regarding the machine learning. So for which types of machine learning could be used quantum computing? So for task, is it possible to use it for some kind of regression tasks or for supervised machine learning? Or I see that for classification tasks, it's clear.
For the moment, actually, we're working for clustering. we try to do something with the K, with clustering technique. I don't remember the name of the technique. K-means. We're trying to do something with the K-means. We're trying to turn the K-means to quantum technology. We're just in research on that.
Okay, thank you. So I just write it because I don't know.
And another thought is the detection of point anomalies. We're working on that this period. No results for the moment, but we're working on it.
Dear colleagues, could I make some remarks?
Yeah, sure.
If you hear me. First of all, Ilias, thank you very much for giving us the introductory talk. It's very dense time for you, I know, and for us too. We have end of year reports, and this is some kind of introductory talk for you without details, without detailed explaining. And my remark is the quantum computer, I think, requires changing the mind of and way of programming. I'm right?
Definitely.
We choose many tasks from our regular work, and such kind of tasks cannot be solved on quantum computer, I suppose. And first of all, for next our cooperation, we can choose correctly the type of the tasks which we can solve on quantum machine. It's the first point, I think. And the explaining of results can be, for explaining the results, we can make in regular statistical way, and we must use the quantum computers to give us the sometimes of high step. I think I imagine the calculation as a high step, not regular sorting, not regular queuing of tasks. And what is, in few words, can you explain what is the way of thinking in computing programming? How can you explain? It's not a regular stepping of procedures. It's some kind of different task. What we can change in our mind to be prepared to quantum computing? Difficult question, Ilias.
It's difficult question.
Switch to the slide 12. And it's some type of not general programming way. I'm programmist, I suppose, and I understand the different ways of programming, the imperative programming, the functional programming. It's not an imperative, it's not a functional programming. What is the way, how to be prepared to choose the tasks and solve and then explain the results in general, maybe statistic way?
First of all, it's something quite different. We have to think different, in a different way. For example, the first steps is to understand that a qubit is at the same time 0 and 1. The second is to understand the gates we apply, which is different than the normal gates we apply to the normal classical machines. And finally, programming, again, we will use language like Python. But in the point that we are going to use the quantum, then we go down to circuits and gates. Yeah, it's different. It's not. You cannot say it's a functional language or a normal language we know up to now. And I don't know. Our problem here was that if it is okay to spend a lot of time and put a lot of effort to turn our research to quantum, and actually, I can't answer that question up to now. I'm not quite sure if it's worth it. Really. We're still working on it. We will see. We don't know yet. The only thing which is interesting again,
the probability can be different too. We can choose several measures of probability in the mathematical meaning. I mean that not the probability in general way. We can choose the probabilities of an imprecise probability, I suppose, can be used, imprecise probabilities, interval probabilities, not only point probabilities.
I'm not talking about point. Okay, now I understand what you are saying. Yeah,
tell us about the exact, also approximate probabilities as a point probabilities. We can use probability in interval, I suppose.
Yeah. Okay, now I understand.
Okay, or imprecise probability with different measure of probability.
Yeah.
Functional measure, I mean.
We can test it, but what I mentioned before, and what is the most important for me is, first of all, if we want to do something with quantum, or not with quantum, with any computing device, the first thing is to understand the problem.
Yes, of course.
This is the most important.
That is the main problem, to correctly understand what we can do on the quantum machine and which type of data we can use and how we can explain the results.
Yeah, for example, we cannot use a quantum machine in order to add two numbers. It's ridiculous. We will have very nice, very good classical machines. And can we add two numbers with quantum? The answer is yes, but there is no reason to do that.
Yes, in spite of this fact, I could ask maybe your research and from my side researchers, what is the type of tasks they want to be solved on quantum machine? So maybe the question is to think about it. What is the type? The type of tasks, how can be reduced in time, how can be...
Yeah, this is the main point, Andrei, to reduce time.
Yes.
But up to now, I don't think that we can reduce time with this quantum machines that we have.
And in spite of this, I would like to ask the participants to exchange our minds about this.
Yes, I believe that we can do it again in a more not so formal conversation, and to see that if there are topics that are interested in us and or are of interest of you. And for example, okay, for machine learning, we try to apply some machine learning techniques. I don't know if they are useful for you, for example. K-means clustering, for example. I don't know if you want it, or point anomalies. But on the other hand, if you have applications, we can probably help ourselves and you to see that, okay, this is a nice application. It's okay to work and put effort and spend time on that in order to gain something better. than we have up to now.
Oh,
But
yes, it's
said,
better way to formulate what we can choose and solve from our side, and how can be it solved from your side, researchers? Is it okay?
yeah, you mean from the theoretical point of view, the mathematical point of view?
Maybe in theoretical point of view, and we can understand what we want to be researched and what can be solved on the quantum computer, I suppose.
Something else before we close. Do you think that this possible collaboration on PhD is possible?
Yes, of course.
Okay, thanks.
About master's degree, it's possible too, and so many topics we can discuss not this time and later.
Okay,
Thank you, Ilias.
I thank you. How's the weather there?
It's snowing. It's snowing, but snow is melting. I see onto the window and see the snow. Snow is melting. It's above 0 on Celsius now.
It's about 10 here and raining.
Okay.
Okay, dear colleagues, maybe one more time we thank our speaker for it is interesting talk and stimulating discussions, because really when we enter completely novel field, one need to think, and we just have several days and maybe even weeks during Christmas holidays to think. And then we communicate with you, Ilias, discussing the possible date of our, let's say, workshop, seminar, not workshop, but seminar, describing what we are doing here and what could be task from our field of view. But also my idea is that we do not need to limit ourselves only to quantum computer. In this supercomputer modeling, etc., there are still a lot of plenty room even in highest output computer, and then we could discuss our collaboration in within this more standard field, but there are still a lot of gaps that could be solved by our possible collaboration. Okay, thank you very much one more time, and be safe and healthy.
I thank you.
Okay, bye-bye. Thank you,
Bye.
everybody.
Thank you.
Thank you very much.
Yeah.